Yes, ma'am.
Okay. I think most of you have joined, so we can start. Okay. Uh, so okay. Uh, so yeah, last day we were discussing about different types of attacks, and we have given a very general overview. Then like we were talking about this type of attacks, right? Uh, like we have talked about this, what we mean by this malware, the brute forcing it straightforward, like you are trying all the options. Then memory buffer overflow, I will talk a bit about this buffer overflow. There was a bit confusion, I will come to that. Then how this ARP spoofing, then we talk about MITM, then DNS poisoning, and indirectly these can lead to some session hijacking. Now, this part we will again discuss. I mean, exactly how we can implement and in practical scenario how it can be realized. That we will talk about when maybe next week when we'll talk about CAN security and its solution. There we will see some predominant example of this type of MITM attack. About this memory buffer overflow, there was a confusion. I should get that first, then I will come to this. uh, uh, Last day I was, yes, okay. I was talking with this. We have started discussing with about this buffer overflow. There are two things. That is, we have discussed this partially because this is a very important attack, and we had a plan to show a demo. You will also work out on the demo. That will be your assignment will be related to that, and we will discuss much about this buffer overflow. How, what may be the because this type of attack, it was proposed tentatively on 2001. Okay, so in between there are some possible solutions to how to prevent this type of attack. And especially someone was asking about how to identify the target address, etc. So what maybe how we can efficiently use some no operation, and what is that the effect of that particular NOP function, and what is the relation of that function with this buffer overflow. So all these things we will see, that we will discuss in detail along with that demo. Okay, so but today it is not possible because we are going with a campus lockdown, so there are some restrictions on going be working in the lab, etc. So maybe next week, Friday, Thursday or Friday, we will do that. Okay, but there was one small confusion from my part. I mean, last day because this is because if you see this diagram and this diagram, you can see the growth is shown in two different direction. Okay, maybe I don't know, someone was trying to point out, maybe he or she was telling about stack should go up or down. But I will request that do not use these words that the stack should go up or down. Always try to use stack grows. When we talk about this type of stack, that grows from higher address to lower address. Okay, so whenever you are drawing this type of stack, system stack, program stack, in this type of buffer flow context, you are explaining that. Always remember that you should mention the higher address and the lower address clearly. Okay, if you do that, then there will be no such confusion. If you do that, then the first function you are calling, that is the first function that is first allocated to the stack, and that is in the near to the higher address. The same, if you do that, these two diagrams are same. Okay, so this is high, the first function you have allocated there. Now the next return address, this return address this is related to the return address related to the main. Like when main function, it is, this is related to the space for the main's local variable. And when the main function, we are completing the execution of the main function, this will be the return address to go back. Okay, so PC will go to this return address. Next comes the function you are calling, that is the area function, maybe shown here as the A function. So that is the A's local address space, where local local variables are getting stored here. And when we are talking about the return address related to this function A, that should be come here. Okay, this will be the return address. Last day I was thinking this high is this direction, that's why I had a confusion. So whenever you are thinking the buffer, if the buffer is in your this second function, maybe here it is the area function, and when the overflow will happen, then this growth will be in this direction. Okay, so this return address will get covered. Okay, and if you are considering the buffer is in your main function, then the growth will be in this direction. Then this return address will get corrupted. Okay, so this is always remember in which direction you are showing the high. Hello, am I audible? There's some. Hello. Awesome. Hello, am I audible?
Yes, ma'am.
Yes, ma'am, you are audible.
Okay.
Yes, ma'am, you're audible.
Yeah, there's some problem for me. Okay. So always that was a confusion. So whenever, if you are showing high in this direction, like this is your high address. Okay, this is your high part, and this is your lower address, and your stack is going from this direction. This allocate the main accordingly. Then the next address will be your main's return address. When the main function is getting completed, this will be the first bit. That will be the return address where the PC will come. And after that, this is the the next address, next function, what main is calling. Related to that, those variables will get stored here. This is the area part, or A function, what we are pointing here. And then A's return address will be stored here. So always point that correctly, high to low, and show the stack growth accordingly. Okay, then there will be no confusion. So that way, when we are considering the buffer in A for within area function, then the growth will be this in this direction. So there was a confusion. I don't know. One second. Yes. Okay, so this is about the buffer overflow. The same thing, if you just follow that convention, in both the slides, the diagrams, you will find the similarity, you will understand the similarity. Here also, this is the same thing. Okay, so this is about the confusion in the last class. So anyway, so last year we were talking about these type of attacks. Okay, now in the one second, in the shared folder, now you can check that I have uploaded the class slides, and along with that I have uploaded this paper. Okay, this is the paper. You can start going through this paper. That is the survey discussion we have started with. Okay, here you will get the reference of different types of different domains of cyber security. First of all, different domains where cyber physical systems are getting used in a huge way, and what may be the security consequences, what may be the possible attacks, possible vulnerabilities in different domains. So here you will get the relation between the CPS system, CPS components, and security issues. So to study this, basically we have started discussing this paper, and to study, to understand these different vulnerabilities, there are different terms you will come across. You will come across the names of these terms. What is, I mean, malware, this type of ARP spoofing, this type of buffer overflow, etc., etc. So that's why we are first discussing these types of attacks, what may be the different types of attacks, so that when we will get these terms in this survey, you will not get confused. You will have some idea that with that name, what type of problem or what type of changes are possible, or what type of threats are coming into the system. Okay, that's why we have discussed about this type of attacks. I mean, and then we will again come back to this different types of domain related discussion, like what may be the problems in smart grid, what may be the problems in medical device, etc., etc. We will come back to that later on. Okay. So this is the start with this paper. So related to that paper, we have started the discussion, and then understand the types of attacks, what we mean by different types of attacks. And then again, next day, tomorrow also, we will come back to the domain specific discussion. Okay. So in continuation to this types of attacks, today we will discuss another typical comparatively modern attack, because yes, where what we are trying to discuss here, we are trying to flip bits. This attack is targeting to flip bits in your memory without accessing them. Okay, now for that also there are different types of strategies. We have one, use some other type of laser beam injection policies are also there. We will also mention that, but this is a very comparatively new attack, because this type of, maybe this buffer overflow, it was proposed around in 2001. Then if you are thinking about DNS poisoning, these are also quite known for few days, for few years actually. Now you've come to this, if you come to this side channel based attacks, this also we will see with an example later on. What happens here, when some algorithm is running in your system. Okay, now from there is some power information, there is some timing information. When you are giving different inputs, your same algorithm may take different, may have different requirement of timing. So these, with these variables, power information, timing information, based on that, some leakages are possible, and those information can be used, can be collated together, and can be used as an attack vector to your system. Okay, so we will take a separate example to understand this side channel based attack. But the important part is that this is also, if you see that 2009, 11, 12, 9, 10, even before that, those papers, that time was also the side channel attack was very much prominent. Now also it is very much prominent, but the actually, at least the idea was known. Now what we are going to talk to today about this flipping of bits in memory without accessing them. These type of paper, it came into picture around 2013, 14, and prominently implementation maybe after 15 or so. So comparatively, this is comparatively a new attack. Okay, so first let me explain that what we are going to do in this attack. First we will come to this diagram. Okay, then I will go back to this slides again. So where here we are focusing on the DRAM part of our design. Okay, in first we will just recap quickly that what happens when a DRAM cell, it stored bits, like when we understand that when we are storing 1 or 0 bits, when we are trying to read or trying to write to some DRAM cells. Okay, what is DRAM? Anyone?
Dynamic RAM.
Yeah, I mean, what is the basic difference between DRAM and with SRAM?
Ma'am, like in dynamic RAM, what happens is the storage speed, the speed of storage is less than that of static RAM. And
Okay.
Ma'am, you have to continuously refresh the cells.
Yeah, that is the problem. Okay. I mean, what is the advantage of DRAM? What is the advantage of SRAM? What are the disadvantages?
Ma'am, DRAM is cheap and SRAM.
SRAM is costly, right? And faster. SRAM is faster in
Yes, ma'am,
comparison
SRAM is faster.
in comparison to DRAM, right? So from this, at least from this, these two diagrams, it is evident that DRAM is comparatively comparatively cheaper in comparison to SRAM. Okay, so here we are not going to the discussion of SRAM. We will quickly recap that what happens in DRAM, just basic storage and basic read write, and from there we will understand what is the basic idea. Then I will come back to this. Okay. So when we talk about this DRAM, most of you, I believe you all know that what we have. Let's start the idea of the basic transistor, nothing else. This is the gate part. This is maybe source. This is your drain. Okay. So when there is a significant voltage you are applying to this gate, then there is a possibility of passing information. If you think in terms of information, and with this drain, if you are attaching one capacitor, then this DRAM, this cell, this can act as a 1-bit memory storage, right? Okay. So here, if this capacitor is charging, it is this way it is storing the 1 bit when this gate is on, and also maybe some voltage beyond a certain threshold in this source part also. Similarly, if you are just blocking the gate, then this way, if it is your transistor, again, if we are blocking the gate, this is the source part, then there's the transistor may discharge, and then the state of the cell, we can consider that as it is storing the bit 0. Okay. This is the general idea of how DRAM is acting as a 1-bit memory cell, 1-bit memory storage. Okay. Now we know that when we are talking about, in today's IC, today's circuits, today's embedded system, 1-bit DRAM cell we are not working with. We are working with these type of multiple DRAM cells arranged in rows together and arranged in columns together. Basically, we are talking about that they are very much closely connected. They are very much closely placed cells, these DRAM cells. And when we are placing them closely and when we are performing some read and write operation, then there is some flip side of that. And this attack is basically exploiting that flip side. Okay. So we will see that in step by step. Okay. So what is the arrangement? Maybe if we draw a clear picture like this. Okay. One second. Just a second. So when our huge amount of what happened? Yes. Huge amount of memory cells, what was it, DRAMs are arranged. They are generally arranged in this way. They are arranged in the blocks. When these rows, if we just visualize them in a bit detail, we have this type of structures, right? So we have the multiple DRAM cells. They are arranged side by side. And this line, this is, we term it as a word line, and this we term it as bit line. Okay. Now what happens if we are trying to read values from this memory cells? Okay, that we cannot do separately, because reading or writing some values in the memory cells, that is not a very easy process. For that we need some extra circuitry. We term them as sense amplifier. Okay. Now what these same sense amplifiers do? These sense amplifiers, they are connected like this. They are connected with, this is one bit line and this is another bit line. They are connected to two different bit lines. Okay, these sense amplifiers. Now what happens when we are trying to read some value? Just think about the read operation from this dynamic RAM cells, DRAM cells. We set these bit lines to a certain voltage. Maybe in general, that is the half of the voltage that we generally use. That is the maximum voltage you are using. Compared to that, we are just raising this bit line to a half of the voltage. Okay. So what happens if you are using, let's say, 3 volt in general? These bit lines you are setting to 1.5 volt. Okay. Then what we are doing these word lines, we are setting to some high voltage. Okay. That means now this get part is on, and based on whatever values you have stored initially, there are multiple such rows. Okay, this is not a one row. I have just showing you one row just to understand. Let's say you are trying to read something from this dynamic RAM, the value from this dynamic RAM. So this word line voltage, that is raised to, let's say, some high voltage. Okay, now this part is on. Now based on whatever you have stored before in this capacitor, this is the capacitor, whether it was in state 1, okay, there will be small discharging in this part. If it was, let's say, this is in state 0, then there will be some charging in this part. Okay, that means whenever you are raising the voltage of this word line, and initially you have set the bit voltage to some nominal voltage, this bit line voltage. Now there is a change. That means this capacitor is either charging or discharging. Something is going on, some change is going on. There is a change in this bit line voltage also. But this sense amplifier, this particular block, it is not connected to just one bit line. It is connected to another bit line in also. We have two bit lines together that is connected to the sense amplifier. Now that bit line also was initially holding 1.5 volt, and there is no change in voltage due to this discharging or charging. So in that way, there is a voltage difference between this bit line and this bit line. Correct? So in this way, due to this difference, so now say the sense amplifier can sense that yes, there is a change between these voltages, whether there is a drop, there is a charging or discharging. Based on that, it can sense what it can read basically. Sensing means here it can read basically what was the bit stored before in this DRAM cell, in the cell block. Okay. So this is the basic strategy how reading of one bit is possible from this DRAM cell. But ideally speaking, this generally this reading does not happen is just from one single cell. It happens in rows. Okay, these whole rows, this operation, this reading operation can be done together in the whole rows, in the whole rows. Along with that, there is a second process that when we are talking about this reading of values from this dynamic cell, of course subsequently there is a, because there is a discharging. Okay, so capacitor part is actually losing something, so that's why immediately there is a requirement of charging. So whenever there is a reading process, back to back there is a charging process, or what I should say, there is a writing process in the cell itself. So this goes on simultaneously in DRAM cell blocks. Okay, that means, in short, what I meant to say, whenever we are trying to read one block, it is not possible in general to read the one block. We are basically reading one rows together, and then we are again writing back one rows. Okay, for to write another to the row again, what we have to do, we have to change this voltage, this word line voltage. We have already set it to this the high voltage, and according to that we will based on the requirement what bit we are going to write, there will be a toggle, there will be a change in this voltage, whether maybe we can keep it high, or there will be a, or maybe based on the what type of bit we are going to write, based on that there will be change on this word line. So this change, and once that is done, once one row is already read, this whatever you have stored, whatever you have written, if you go back to this diagram, here, whatever you have written, you have to, the cell should store that. For that you have to disconnect this word line. Okay, now this is a process. If you now think what is going on in this read and write process, initially this word line is set high to a specific voltage, and then when this reading writing is over, again we are connecting this word line. Okay, this is a standard process. Now while doing that, of course, if you observe, there is a toggle of the state of this word line, right? There is constant toggle of the states of this word line. This is the first thing. Okay, another process is that is called the refreshing of dynamic cells. It requires constant refreshing, we say, but constant means there is a specific rate to refresh this type of dynamic cells. There is specific interval by which all these cells should get refreshed. What is the interval? Do you have any idea what is the interval in general processes? What is the interval to refresh this DRAM cells? Anyone? Okay, this is typically 64 nanoseconds. Okay, so there is a so the time, this is just for knowledge, but time, it is just important to understand that there is a specific delay between one refresh 1 and refresh 2. Okay, because refreshing itself, it's also like setting some values to this word lines, setting some values to these bit lines and doing the refreshing. So that is another process, right? So there is certain delay between these two refreshes, some time lag between these two refreshes. Okay. Now this is the general observation, general implementation requirement, general implementation idea of on how DRAM cells work. Okay. Now what will happen when this, if you are trying to read purposefully a let's say this is one word line. Okay. Particular row, you are targeted, some attacker has targeted to attack a particular memory block, and in that memory block what it has observed that if there is a toggle between these word lines, I mean word line states, then there is some subsequent effect on this connected these rows. Okay, because due to this toggle, sometimes there are different observations. In when we will go by the slide, we will talk about that sometimes some field is getting created, some conduction channel is getting created, and those with those channels, due to those channels, when you are accessing these word line and these bit line cells, that means all the cells, they are connected in the corner of this word line and this bit line, right? So when only this cell or this row you are accessing, you are doing nothing with this row. Then also there is, if there's a huge toggle in this word line or in this word line, then there is some effect, some charging and discharging going on through the cells as attached to this in between word line. Okay, so that means this in between word line, in between line is actually initially idle. There is no access to this memory block. Then also due to the fact that this word line and this word line is getting accessed together, whenever it is getting toggled, the values are getting toggled, there is some some charging and discharging effect on the cells attached to this word line. Okay, word line in middle. Now in general, of course, that is also very normal. That is also nothing new about it. If there is a charging or discharging, we have the strategy of refreshing this DRAM cells, so that refreshment will take care of the charging or discharging. That means that cell will come back to its original state or hold good its original state by this refreshing procedure. But the problem is when this toggle is too much, it's the too much toggle to particular row blocks, okay, of or to a particular row of a memory, to consecutive rows of a memory to be specific. So in that case, what will happen? This charging or discharging speed is also too high. That means it is true that it is known to everybody that these DRAM cells, they leak. There is a, in spite of the fact that gate is blocked, still there is a possible leakage from this DRAM cell. That is known, and for that this refreshing strategy is there. Everything is taken care of. In spite of that fact, when this toggling rate is very high, then this leakage rate is also very high. This charging or discharging, that is also very high. And that way, if that charging is discharging is very high and refreshment is not done, and maybe the cell has leaked all the charge. In that scenario, there is a possibility that if the cell, that in between intermediate cell, if it was holding logic 1, it was storing, that memory cell was storing logic 1, with that discharging effect, with the toggling effect to not this line but this word line and this word line, this bit is getting flipped to 0. Okay, that means this, in spite of the fact this block, this row was untouched, it was never accessed, still it is a possibility that when the adjacent word lines are getting affected, they are toggled too much and they are getting these lines are getting toggled, with a very huge rate, in a huge speed. It's I mean, within a certain amount of time window, it is toggling beyond a certain threshold, to be specific. In that case, these conduction channels, these fields, they affect these intermediate cells or the rows in such a way that there is a possibility of bit flip in these intermediate cells. Okay. Bit flip means you're changing the value of your memory block of a particular row. And that way, this is considered to be a attack to your system. That means, let's say you have stored some critical value, critical data like 1011. Now with this bit flipping effect, it got changed to 1101. Okay, the entered value, I mean, there's a change. In fact, this type of attack, it is nowadays very serious, because this is also getting used to change the authentication, to change the access control. Let's consider for a particular block, for some of the applications, some of the memory part, you have added some access control bit, and the bit value is set to 1. Okay. Now with this bit flip, actually the attacker is not targeting, not touching anything, not accessing any, trying to access. Maybe the attacker is not having any permission even to read the data from that memory block. Then also, if it is possible to read or access data from the adjacent rows, memory rows, then also it is possible by reading, just by reading data. No, I mean, in a the reading speed, if it is it is such that it is higher than a particular threshold, then it is possible to flip the bit in this location, in this memory block, in this memory cell. So that way, if this access control bit is now reversed to 1 to 0, then of course the adversary is now getting access to those that critical block, critical part of data or whatever resource it may be. So that way we will discuss that this is a basic idea of the attack, and today we will discuss the attack only, and next year we will discuss how this attack can be used to change the root password, or to attack against the root password, to attack against the authentication. Okay, so this is the basic idea of how I mean, this attack is planned. This attack is planned just considering this word line. I mean, toggling part of, taking advantage of this toggling part of the word line, and having the knowledge of this charging discharging part of this DRAM cells. Okay, so this is the basic idea. Is it clear, or should I repeat it once again? Hello? Anyone? Is it clear?
Ma'am, when the two adjacent rows are getting toggled, what exactly happening? That word line, and how the voltage is changing, the capacitor voltage. Ma'am, can you?
When first of all, the capacitor voltage. Okay, just a second. See, whenever you have this bit line, right? You have this bit line attached to this. Okay. You have given a high voltage to this word line. Okay. If you have given this high, that means that now this gate on, this pass transistor is on, in the on state. Okay. Now you have set this bit line to some some nominal voltage. Let's say this is half of the voltage in generally it is said. Let's say this is 1.5 volt. Okay. So when this is set, then if this gate is on, then there is a possibility that there is, based on the what value you are putting in this gate, that either if this capacitor was previously holding value 1 bit, maybe that means it was charged, right? Now it is leaking some information here, leaking some leaking some it is discharging, it is partially discharging, you can think. If it is initially discharged, it was holding, if it was holding 1 bit 0, then now it is getting charged a bit partially. That means there is a change in the bit line, because this bit line capacitance, if you go to the internal details of the bit line, that there's also a capacitance that is higher value of capacitance. In that way, there is either a partial leakage, in either way, maybe some discharge or some charging. So that way there is a change in this bit line voltage. Okay. So this partial discharge or partial charging, that can be sensed. That's why we are talking about this. This is the sense amplifier. Okay. This sense amplifier is changing. This is one thing. Okay. This always happens. This is nothing new. But what happens in actually there are different studies. If we can go to this slide, wait. One second. Anyway, I will show that to you. There are three studies. So I have the references. Okay, I will show that later on. So the studies show there are different experiments which shows when this word line is toggling. Basically, toggling means why it is toggling. When this reading part is done, from this the change in the charging, this discharging change, due to that change there is some change in this bit line, and that change is getting sensed by the sense amplifier, and that way this sense amplifier is reading the value, reading the bit that was previously stored in this memory cell. Now once that is done, since this discharging or charging is not desirable, right? You want to, just for read operation, you don't want any change. So that means what you want to retain the whatever was there previously in this capacitor part. So that way, always in general in DRAM part, DRAM read is always followed by a DRAM write. Okay, and once that is done, then and you have just done this read and write operation in this, for this row. Okay, this row you have considered, this row you have done. This row means what? Whenever I'm talking about row, you just imagine there's so many cells. For these every intersection, you have one DRAM cell, right? You have one DRAM cell. Now let's consider you have already completed reading this row. Okay, because whenever we are reading or writing, that is done by in form of in the throughout the row we can do that. So when it is done, we are basically disconnecting this word line. Okay, because now we want to return in the capacitor, we want to return what we have stored. That may be 1, maybe 0, whatever it may be. So whenever we are we are not reading any row, this word line is not contributing anything. Okay, so we are basically disjoining that. Once we are disjoining, that means this word line is again toggling its state. Initially, for write purpose or read purpose, we have set it high. Now we are disjoining it. So we are again changing its state. So there is a possibility of toggle. And when there is a toggle, maybe then this is your row 4 and this is your row 2. Okay, there is a toggle. And for this toggle, for this word line toggle, there are different studies, there are different references. In that, I have already shared one paper, you can see there. From that paper also, you will find the idea that what type of effects are there. There are some EM effects, there are some conducting channel in between, because whenever we are considering these capacitors, whereas whatever components we are considering here, they are not very much perfect, they are not ideal. So always some internal conducting channel is there, or some leakage is there. And when this state change is there, constant state change, whenever you are doing some reading, this toggle is there in the word line. This toggle is affecting that conducting channel, affecting that field also. And that way, this in between row, initially you were not reading, adversary was not touching this row at all, but some discharging is going on in this row, I mean the cells associated with this row also. If that is the case, of course it always happens for DRAM. This is nothing new. This discharging is always there. That's why we have the, maybe that was your question, right? When it happens, the cells are getting affected. Aditi?
Yes, ma'am. Yes, ma'am.
Yeah.
Ma'am,
So,
I was asking if suppose row 4 and row 2 word line, these two rows are frequently toggling, then how come this row 3 is getting affected, or row 3's word line is getting affected?
that is, I will explain one with an example also. That's why I'm telling, when the studies, there are different references that show that when one word line, because when there is this word line toggle, because these cells are very closely spaced. Okay, where they are very close knit. So that way, when there is a toggle in this word line, then the adjacent, adjacent, there is some EM field is developing. I mean, that field already exists, and there is also some conducting channel in between these components. They already exist. Okay, and some discharging that is not for toggling. That is a continuous process. This is happening. But what happens, what I'm pointing out, that when this toggle rate is too high, too much toggling, that means this discharging or charging, this rate is also increasing. And this, when due to this discharging, we have the requirement of refresh procedure in DRAM. So we know that these cells are discharging or getting affected by adjacent rows, adjacent components, and that way, and they are also connected to this word line. They are connected to their gates, etc. So that's where refreshing technique is already there. But that refreshing, there is some, as I mentioned, there is some gap between one refresh and the second refresh, and it was calculated, this gap was calculated, the 64 nanosecond, that if you just refresh this these lines within after 64 nanosecond, then that is fine. Till then it will hold their own state. That was initially measured before this type of attack was there. But now the problem is, by the attack means now this row is constantly getting, I mean, you are just constantly the code is very simple. If you see this, your attacker is doing nothing. I will come back to all the slides. First, I will give you the idea. Attacker is doing nothing. It is just executing this type of code. See the code first. What the attacker is doing, it is writing, it has done some just one survey, some reverse engineering of the memory block, and it has the idea. It is selecting two rows. This is row 1, like here. You know that from this memory diagram, memory block diagram, that you know that these row 4 and this row 2, they are in the same bank. They are in the same block. That way, maybe X is 4 and Y is 2. Now, attacker has selected these two rows, X and Y. Okay. But Not necessarily, and purposefully they are not adjacent rows for the demonstration purpose. In the experiment also, they are not adjacent rows, but they are rows in the same block. That is important. Okay. Now for that to be in the same block, what is happening when there is a toggle related to this block, this Tx, and there is a toggle related to Ty, then the field, this intermediate field, and the related charging and discharging due to that, that is also getting affected. That means discharging or discharging rate of these intermediate cells, that is increasing. If you focus on the discharging rate also, then also we will understand that capacitor is discharging faster. So initially the designers, they have computed some refresh time. Okay, after 64 nanosecond, the cell will get refreshed, and then it will be fine. It was considered. But now what happened? The intermediate capacitors, they are actually getting discharged just around at 50 nanosecond. So before the next refresh, this cell is getting discharged. It is not retaining its original state. Okay. Now next, come to these two steps. This is flushing X. This is about the flushing the buffer. Okay. Flushing the row buffer, because what happens if your data is it is for to flush the cache memory, because once you have taken the values from the DRAM to the cache, of course next time whenever you are executing the same program, it may happen if you have not flushed the cache. So the idea is that your program will fetch the data from the cache. It will never go to the DRAM. It will never first, because when the data is not in the cache, then only it will go and search, then only it will read from the DRAM. So that's why we are flushing the cache. And then this part is called infants. Now this instruction is mainly given to ensure that once this part is complete, this memory write is complete, then only next memory execution will start. Okay. So that way, again, when this code is, again, this is a repetition. This code first read from DRAM, it taken the data in the cache, data in the cache. Again, it is going back, and it is this emphasis ensuring that cache clearance is done, and then again it is going back, again reading. So that way, it is a very frequent read from the same cache lines. When that frequent read in the same cache lines means, again, this is not from the, you may ask that why it is not fetching data from the same, maybe it's only from X. Okay. If it is fetching data from the X, then this word line, what we are telling here from this diagram, what we are telling that, one second. Whenever this row read is done, reading and writing part is over, this word line will get disconnected. So in that case, if this reading and writing from a particular row, memory row is not over, then of course we cannot guarantee that this word line is got disconnected. So if this word line is already connected, then this toggling will not happen. Okay, and if the toggling will not happen, the EM field or the conduction channel that was formed with the next level rows, they will not, discharging or discharging rate will not get affected. It will remain same. It will remain same, and it will be the discharging, whatever discharging was going on, it can be handled by the next level refresh. So that way, that's why it is important. That's why it is important to clear the flush. I mean flush the cache, And also ensure that once that flushing of the cache is done, then only next read operation will start. And that will be not from the same, because this is the same thing. See, this is the code 1B. And there's a discussion that if you just execute this code, okay, the same thing, in the same rate, you are just calling this rows, but you're calling the rows from the same memory row. So in that way, that will not affect anything. That will not change any bit in the memory, because it is not disturbing the intermediate EM field. It is not disturbing the intermediate conduction channel. And that way, it will not affect the intermediate rows. It will not affect the intermediate rows because there is no toggle in the word line part. Okay, so this is a basic idea of, that's why basically what we are doing, we will start again from, we are basically affecting this part. So that is from here the name of the attack comes. We call it as row buffer, row hammer. We are hammering to this row buffer part. We are repeatedly changing values in this row buffer part, and that way the intermediate, there is a possible flip in the intermediate part. Okay, so this is the basic idea. So if you go here, there's already a result shown that this attack was initially tried and tested. This is the initial paper. Later on, it was tested in different types of DNN accelerators and different embedded processors. Initially, it was tried on this type of few Intel and AMD processors. Okay, and these much of flips was observed. Huge amount of flips, you can see this was observed only due to this issue. Okay, so is the basic idea, is it clear?
Ma'am, could you please explain that code 1B again?
Yes. Okay, yeah, actually what I will do next day, I will go by the slides also step by step. Then first you think about what the code is doing. First is move X. This is basically read operation. You are moving this X block. This is the X block in the memory. This is the this is your X row. This is your Y row. You are taking the data from, maybe you are taking the data from here, and you are taking the data from here. You are reading that to your row buffer, the row buffer or sense amplifier, whatever name you call it. Yes. So initially there is a movement. When you have read the value from this X, there is a movement, there is a change in the word line value, word line set. Initially high, then it got disconnected, so it's set to low, so there is a toggle. Okay, why there is a toggle? There is no requirement of toggle here in this code B, because you are fetching the data from the same word line. So we disjoin the word line according to the convention. The disjointing the word line is done only when we are moving to the next row or other row. Not only next row, we are moving to the other row. So when this move Y, basically then we are hitting some other row. Okay, we are same way we are taking the data back, data to our row buffer. We are our sense amplifier is reading the data, etc. That's whatever steps we have discussed before, that is going on. Okay, now once you have read what is the importance of these two lines? Now when you have read these values to this cache, you read this values from DRAM. Of course, the first thing what general processors do, they will store the data in the cache. So next time, whenever you are using the data, it should first search in the cache. If the data is there, it will take from the cache memory, it will process, and it is done. So if you do not use these two lines, again, this attack will not be successful. What these two lines are doing, they are clearing the flush. Okay, they are clearing the cache memory. They are flushing the cache memory. They are flushing the buffer. So that way, now when next time, again, emphasis, and this is confirming that all these operations are in order, right? This is it is waiting to complete these memory load store these operations. Once it is complete, then only it can proceed to next level operation. Okay, once up to this part is done, again this code is jumping to initial, this code 1a. See, this just jump code 1a, it is jumping to this initial location. That means it is again starting to this from this step, move step. Okay, so for this reason, what is happening, again the same process is starting. Again, your program is searching for this x value. It is trying to read maybe from this x value related row. Now you have to, as we already discussed, when we are reading from a dynamic cell, we can read from the cell only. We have to read the row, so that again the row is going to the based on the row values, we are setting the bit line, we are setting the word line, and there is a change based on the discharging and discharging. There is a change in the bit line, and this change is sensed by the sense amplifier, and sense amplifier is again reading the value x. Again you are moving to row y, so you have to disjoint the word line. Again there is a toggle. So now when this code you are running too fast, that means with your high system clock, you are running this code, and for a short duration, within a small window of time, repeat a huge number of times, your this row is getting accessed, and this row is again getting accessed. That means huge amount of toggle in your word line. And when there is a toggle that is already exists, that is this, for that toggle, for the closed knit effect of these word lines, the change in EM field, the conduction, existence of conduction channel, that is not new. For that, we know there's a possible leakage. We need refreshing the DRAM cells. Everything is known. That's why we have taken this. We have taken the protection, or memory designers, they have taken the protection. But the problem is that when this toggling goes too fast, it is like an attack. It is planned that when this toggling goes fast, just from two rows. See, in general case, in a general scenario, whenever a general programming like you or me, when we are trying to program, what we will want, what we will try, if we want this type of XY values continuously, then we will store them in the cache memory. We will not flush this cache. We will ensure that our data should be in the cache, so that we can access it and no need to go for the DRAM again. But since this is one adversarial method, adversary is targeting this code for an attack purpose, so these two lines are added. It is clearing the data from the cache, so that every time the heat will be in the dynamic RAM part, and due to that EM effect, conduction effect, etc., etc. I will show you the reference again next day. When you are, maybe someone asking that what type of changes are there, etc., we will show that again till the time is up. So that way, so that is the change compared to normal execution, normal program writing, adversarial program writing. Here this CL flush, this function is added purposefully so that your data should not remain in the cache. Because if that data is in the cache, then there is no point. There will be no attack. This is obviously normal execution of program. Okay, so this is the basic concept of this attack. Is it clear?
So code 1B does not induce errors because the word line will always be hyphen in that code. Is that right?
Can you come again? Can you repeat, please?
So in code 1A, we are going to access two rows, X and Y.
Exactly.
Whereas in code 1B, as we will only be accessing one row, the word line of that row will always be high.
Yes, always be open. Yes, it is.
So
Sorry. Yes. So that toggling is not there. If there is no toggling, so there is no such high charging or discharging in the intermediate rows.
Okay, okay, ma'am.
Okay, got it?
Ma'am,
Yes, yes.
ma'am, that means these two words must not be consecutive. This has to be some intermediate words there in the same block.
See, of course, because if there is these will also happen. This is also possible that the discharging, I mean charging, discharging will be in high rate if the toggle is high, etc. In X, if these are two consecutive rows. But the problem is, whenever you are, as I mentioned, that whenever you are doing one read operation, this move is a read operation, right? You are also doing a write operation. Okay, so when these rows are two consecutive rows, nothing in between, so no one is getting affected, because whenever you are reading, you are again writing back to this row Y. Whenever you are reading, you are writing back to this row X. So nobody is getting affected. There is no problem. But in between row, if you think, you are thinking that it is just an idle row. You are not reading means you are not writing back also. And even the refresh time is not also coming into picture. Before refresh, these rows are getting discharged. So that way these rows will get affected, because if there is no intermediate rows, there is nothing to change, right? Clear?
Oh, okay, ma'am. Yes, ma'am.
Yeah. Okay. So any other question? What I will suggest, actually I have already uploaded. Best thing is that I have already uploaded this in this. Okay, I will upload the slide also. I will minimize the slide writing in this that I will upload. And there was one thing. Slides. Okay. Oh no, okay, I will upload that. Okay, this is not uploaded till now. That paper I will upload today. I will upload, and that you can see this paper. Okay, I will upload today along with the slide. Okay, there you can see the. I will again tomorrow discuss some part of it. This is the paper. Okay, so search with this name. So you will get the references also, that there are different studies showing what may be the, when this toggling is there, what are the different, I mean there were different direction of research is there, what are the effect on the intermediate blocks. Okay, is it clear? Have you got the basic idea at least? Any other question for today? If not,
Ma'am,
yes.
Can you please explain that code 1B?
Code 1B. Okay.
Once you go there, like.
Okay. I'm going. Sure. Yes.
Ma'am, like,
Yeah.
so like, why does not induce error, ma'am?
This one, right? Code B you are asking. See.
Yeah, code 1B.
Code B, for code B, what we are telling, when there is a toggle in the word line. Okay. When there is a toggle in the word line, then only that intermediate discharging or charging, that part is getting affected. That is getting faster. The charging, discharging was always there, but that is getting faster with the toggle bit. But when in this case, you are just reading from move X, the same data. That means you are reading the same row, right? Same row means this word line is not getting toggled. When we are toggling, when this word line always get toggled when we are moving to some next row, some other row. Okay, here you are not moving to any other row. That means there is no toggle in this word line. Got it?
Okay.
You can
Okay.
see the change. Yes,
Yeah.
this part is not there. You're ensuring this move X and Y in some I mean, two different, belonging to different rows, but they are in the same bank. So that is the assumption. That homework is, it is done before by reverse engineering. So then you are just fetching one data. That means you are accessing one row. That's why it is not creating the error. Clear?
Yes, ma'am. So the intermediate row will be between X and Y.
Yes, intermediate row is between X and Y, because this is, here is a, maybe the conduction channel. If this is X, this is Y, then here is a between the rows, between cells. Maybe this is some okay. Sorry, 1 second. Maybe you are fetching, these are your memory, I mean cell block structure. This is, you are fetching maybe some X from somewhere here, and you are fetching Y from somewhere here. And we are talking about the changing, flipping the bits of these parts. Maybe flipping here, maybe flipping here, this one. So this should be somewhere in between X and Y.
So let's say if the X is row 5 and Y is row 7, there will be more effect in row 6.
Yes, there will
So
be
will
effect.
there be an effect in row 4 and row 8?
Row 4 and see,
At least a little.
because this, see, toggle is here. That means toggle is here. That means it is propagating in this direction. The effect, toggle is here, propagating in this direction. So in that way, the effect, the changing effect is strong here.
Okay, okay.
Right, this effect is strong here. Of course, there is a possibility that the toggling is getting in, getting affected in these rows also. Okay, adjacent rows also. But when you are for the attack purpose, they have tried these two rows so that the effect is strong here. Got it?
Yes, ma'am.
Yeah. Any other question? Anyway, we can, if there is, we will take that again tomorrow. Okay, we will discuss this one by some slides at least. This attack only, then we will move to some other topic. Okay. Okay, then that's all. Thank you.